Okay, here we are for simple harmonic motion problems. Okay, we're going to take a look at problem 8. Problem 8 says, let's see here, a 2 kilogram mass is attached to a spring and placed on a smooth horizontal surface. A horizontal force of 20 newtons is required to hold the mass at rest when it's pulled 0.2 meters from the equilibrium position. Okay, which will be the origin there. So you say, so I've got it pulled that far and it's holding steady. So that's telling me how hard the spring is pulling then, right? It's pulling back on me with 20 newtons when it's been displaced 0.2 meters. We're then going to let go of it when it's at 0.2 meters, and it's going to undergo simple harmonic oscillations back and forth, back and forth. They want us to find a bunch of stuff. Force constant of the spring is the first thing. Okay, and that's what that first bit of information is about, telling us how hard the spring is pulling when we're, which is how hard we have to balance it out with, right? When it's pulled that far, that's specifically so you can find the spring constant. So let me jot this down on separate paper. All right, problem 8. All right, again, we have this thing, right? Maybe there's the equilibrium position, right? But we've gone and we've stretched it from there. So that when it's over here, right, we've stretched it a distance of 0.2 meters. So 20 centimeters, yeah. Okay, and at that point, we know that the force from that spring that's 20 newtons that we have to balance against there, right? So I'm just going to go ahead and do a nice, real quick finding that spring constant. We're going to say, hey, formula for Hooke's law spring, force is negative kx. We know now that the force there is 20 newtons, trying to pull us back to the left when our displacement is to the right, 0.2. Right. And the thing is, spring constants are always reported as a positive value, right? So, I mean, technically the spring's pulling to the left would be negative 20, right? K's are always constant, always positive, I should say. Rearranging this. So I'm basically just going to do 20 divided by 0.2, which is like a fifth. That's going to be 100 newtons per meter for my spring constant. Okay, part B. Now they'd like to know the frequency of the oscillations. Okay, they asked for the frequency, not the angular frequency. They want frequency. And so you say, well, they did tell us some more information. They told us the mass was 2 kilograms. Yeah, that's enough. And so we can say, I'm just going to use my formula. Period is 2 pi root m over k. We just found the spring constant. They told us the mass. That's everything we need to know the period. And the period is 1 over the frequency. So you're going to say, okay. Finding the frequency, I'm just going to rearrange this and say frequency will be, 1 over 2 pi root k over m. Yeah. And so I can punch in my calculator. Okay. Root 50 divided by 2 pi. And I get that my frequency is 1.125, rounding there, hertz. Okay, oscillations per second. 1.125 per second. That's what hertz means. All right, moving onward. That takes us to part C. Part C, they say they'd like to know the maximum speed of the mass and where does it occur. So you're going to say, well, the maximum speed. I'm going to say, I know that when my energy goes back and forth between kinetic and potential. When I'm stretched all the way here, all the energy is in potential, and then when I'm back to equilibrium, that's when I'll be at max speed, and that's when all the energy will be in kinetic, because the displacement will be 0. So the force of the spring is 0. The energy stored in the spring is 0. It's all in kinetic at that point. So I can basically say, hey, E max, or rather E total, is going to be the kinetic energy maximum, which will equal the potential energy maximum, 1/2 mv max squared, right? Kinetic energy, 1/2 mv squared. And maximum potential energy is 1/2 k amplitude squared, right? Maximum position squared, right? And you say, well, the maximum position, that's the amplitude. That's where we let go. We let it go from. We let it go from 0.2. The k we figured out was 100. The mass we know is 2. Like I can solve that for Vmax. Bam, bam. 2, that'll be 50. Vmax squared is 50 times 0.2. 0.2 is a fifth. It's going to be 10. It's going to be the square root of 10. What would be my Vmax? And you say, hey, my calculator, square root of 10, 3.16. So my maximum velocity is 3.16 meters per second, rounding off there. Okay, annoyingly, when I did this calculation, you see how we've got, elastic potential energy, 1/2 kx squared, and we're at the amplitude, so amplitude squared. The problem is when I did this line, I left the square off. Oops. So the calculation that I did was going to be off by a bit, by a factor of 0.2. So I got to square that. And so this next line is going to be by 0.2 squared. So it's not going to be the square root of 10. It's going to be the square root of 2. All right, so it's going to be root of 2, right? Which is like 1.414, right? All right, there we go. All right, part D. They want us to find the maximum acceleration and where that occurs. Well, we know that the maximum acceleration is when the force is maximum. That's when it's at the maximum position, at the amplitude. And we can easily solve for that force using Hooke's law. So we can say F max is negative Ka when amplitude is max. The maximum magnitude force will be in the negative direction, but good enough. So you say, yeah, that's just negative 100 times that amplitude, which we know is 0.2, which is a fifth. And so you say that's going to be 20 newtons to the left, or 20 newtons to the right. Same thing will happen at the other amplitude. It'll be 20 to the right then. Either way, you want the magnitude of the maximum force. I'm sorry, this is the maximum force, isn't it? I'm sorry, they wanted the maximum acceleration. Okay, that's easy. Once I have the maximum force, I'm just going to say that F is ma, right? So that 20 is my mass of 2, and that's the maximum force. So that's the maximum acceleration. So 10 meters per second squared is A max. Okay, and then part E, they want to know the total energy of the oscillating system. Dude, didn't we find that again? We already did, right? Total. We just got to plug some numbers in here. Hey, this is the total energy is when it's all in potential energy. We know that's at the max here, so we know it's this. So part E, my total energy is equal to the maximum potential, which is 1/2 100 times 0.2, which would be 100 times a fifth is 20. 20 divided by 2 is 10 joules. Okay. All right. So then when I went to do part E here, I was, of course, using the value from before where I had forgotten to square. So when I calculate that E total, it's got to be 1/2 times 100 times 0.2 squared. So that'll be 50 times 0.2, which we know is a fifth. So 50 times fifth, that's 10. But then I got to do times a fifth again. So it's actually going to be 2 joules, right. So it's got to be 2 joules, not 10 joules. All right. Okay, just like this was 1.414 meters per second. Okay, and then part F is going to have that same mistake carrying on into it as well. See at part F. They'd like to know the speed and the acceleration when displacement is at 1/3 of max. Okay, so now we're going to do a legit calculation, and I didn't leave myself enough space. Am I going to jam this into the corner of the paper, or am I going to get myself some fresh paper? All right, I'll get myself a fresh piece of paper. All right, so here we go. So what I'm going to do, part F. So we're going to say we're at a third of the amplitude, a third of the maximum displacement. Now the amplitude we know is 0.2 meters. So we're going to talk about when x is a third of 0.2. I know, you're like, you should be able to do that one in your head, but I'm just going to do it this way anyway. Okay, 0.066666. Okay. Yeah, that's really, you know what that is. It's 1/15th, right? Isn't that 1/15th? Okay. Let's just make sure I'm not crazy here. Yeah, 1/15th. So it's at 1/15th of a meter. Okay, so what I can do is, since I know that the total energy is the kinetic plus the potential, right, at any time, right? I've spent a lot of time here looking at when it's all the way at the amplitude, or it's all the way at, or when it's at equilibrium, because then all the energy is one type or the other. But now we're looking at it in the middle of a swing, right? And so what I'm going to do is I'm going to say, well, that total energy, though, is still 10 joules, what I found in part E. Now, I'm going to have 1/2 m times that v, that velocity, whatever that velocity is there, plus the potential energy there. The potential energy is 1/2 k x squared, right? For energy in Hooke's law spring. So basically it's going to be 1/2 times 2 times that v squared plus 1/2 times the spring constant was 100 for this, yes? Yes. And the position we're at is 1/15th of a meter. So I can solve for that velocity right there, okay, using energy. If I go ahead and do that, let's see here. Am I going to, half times 2 is just going to be 1. So it's going to be 10 minus this mess. Yeah, let's do that out on the calculator. 100 divided by 2 divided by 15 squared, right? And we're going to do 10 minus that, right? And that's equal to v squared. So I'm going to take a square root. So that v is going to come out to be 3.127. All right, so here we are for part F. Again, you see here, I put in 10 joules for the total energy, which we'll recall is not the actual value, because the way I forgot that square way back then, it's really 2 joules. So this needs to be 2. So when I do my calculation here, let's see here, let's give that another try. We're going to have 2 minus, I'm going to subtract that over, let's see here, 0.5 times 100, that's going to be, or sorry, half times 100 is going to be 50 divided by 15 squared, right? Okay, and then I'm going to multiply, then the half and the 2 are going to cancel each other out. So I just need to take a square root of that. And I get 1.33333. I get 1 1/3 meters per second. Okay. All right, for my answer for part F. Okay, and I think that's the last part that's affected by that mistake I made, leaving that square off way back in part C. All right, so just messed up C, E, and F. All right, you know, these things happen. All right, cool. Okay, so that's the velocity inside a third displacement. They want to know the acceleration at the third of the displacement. And again, I'm going to find that from F equals ma. The force is negative kx, right? So that A is negative k over mx. So that's 100. The mass is 2. And the position we know is 1/15 of a meter. So 100 divided by 30, 3 1/3, of course. So 3 1/3 meters per second squared is the maximum acceleration. All right, that was part G there. Okay, or rather, that's the acceleration when it is at a third of the displacement, right? Yep. All right, and that is it, right? That's problem 8.